Dr. Dan Cayan, who is a research meteorologist at Scripps Institution of Oceanography, University of California, San Diego. His research is aimed at understanding climate variability and changes over the Pacific Ocean and North America. His specific interests concerned impact of climate changes on water resources and other sectors in Western North America. Cayan co-heads the California-Nevada Applications Program and has contributed to the California climate change assessments, which are delivering improved climate information and forecasts for decision makers in the California region. He's a member of the committee which produced National Research Council Sea Level Rise for the coasts of California, Oregon, and Washington, past, present, and future, and the California Protection Council Working Group, who produced in 2017 Rising Seas in California, an update on sea level rise science.
Thank you, Dave, and hello again, everyone. I'm one of Ron's colleagues at Scripps, and well, Ron is a coastal process scientist. I'm a climate scientist, so I'll give you a little different spin. Some of the information is pretty similar, but sometimes it helps to have multiple perspectives. The sponsors that I work under range from agencies in the state of California to federal agencies, and I should say that there's a number of colleagues that I work with that, of course, have contributed to the work that I do. Also, what I'm going to show to some extent is the result of committee work that underpins assessments that are being conducted for the state. So you already saw this curve. Ron described this really remarkable transition of sea level from the sort of pinnacle of the last glaciation to today, and we saw again a change of not a few meters, but actually 120 meters or so from the last glacial maximum to today. And as Ron was saying, that's a change that occurred in response to temperatures. Of course, temperature is kind of an index for climate, but temperatures that were roughly 6 degrees Celsius warmer, cooler than today. And you know, if we treat this as kind of a linear system, that means for every degree Celsius of warming, potentially there could be 20 meters of sea level rise. Now, that's a vast simplification, but at least it gives you kind of the sort of yardstick that this game is being played under. This picture, I have a lot of busy work on these slides, and that's meant to inform people that want to look later. I don't expect you to absorb all this right now, but over 95% of the Earth's water is harbored in the oceans. It's salt water. 3.5% of the Earth's water is fresh water. And over half of that fresh water, which is terrestrially located, over half of that is this frozen ice. And as Reinhard mentioned, over 70 meters of equivalent sea level is housed in those stocks of ice, which are largely in Greenland and especially Antarctica. Let's see, another interesting fact is that under today's climate, roughly 10% the Earth's land area is covered by ice. Under the peak of that glacial period where sea levels were much lower, in other words, there was a lot more water that was housed in this land ice, over 30% of the land surface was covered by ice. So we can see in these long time scales, there's been vast swings of ice from the oceans to the continents, which represent only really a tiny fraction of the water in total that's housed in the ocean. But those little fractions, of course, mean a lot as far as the ups and downs of sea level. So it is a dynamic system. The interesting thing, of course, is that we're seeing these changes now. This is carbon dioxide here, the larger graph, similar to one that Ron showed, and he mentioned that Charles Keeling's measurements started here when CO2 concentration in the atmosphere was 320 parts per thousand, and now it's up here. So it's increased by 40% over what we know is the pre-industrial concentrations. We know those pre-industrial concentrations because the ice in high latitude ice stocks actually have captured gases, and they can measure the concentration of CO2 in those from those ice cores. So we have a very accurate depiction of what CO2 looked like in the ancient atmosphere, and Ron actually showed you a picture of the fluctuations of CO2 over hundreds of thousands, maybe millions of years. And the point of that exercise was the fact that in none of those fluctuations of paleoclimate did we see concentrations exceeding what we've got in this curve in the period before human influences really started to take hold. The other thing, of course, is that there's other greenhouse gases in the atmosphere, methane, the fluorocarbons, and so forth, and they've all increased in their concentration in the atmosphere a lot. The carbon dioxide gas is an interesting one because it has a really long lifetime in the atmosphere. It doesn't wash out. It has, it's reckoned that it takes more than a century for it to start to decay. So what we load into the atmosphere from fossil fuels, and of course, fossil fuels means carbon that was buried, that's like oil or natural gas, that's now being released and put into the atmosphere, is going to stay there, and it's kind of like growing credit card debt, and it keeps compounding. It's a greenhouse gas because it's not transparent to the terrestrial radiation, the infrared radiation, which cools the planet. So it's creating a problem, and that problem right now is to the point where the Earth's energy budget, the amount that's coming in from the sun, is not being balanced by the amount that's going out because of this essentially this extra reservoir, increasing reservoir of greenhouse gases in the atmosphere. And we're out of balance right now, less than 1 watt per square meter of the Earth's surface, which doesn't sound like very much because, you know, the light bulb here is probably 200 watts or something, judging from the blinding that I'm getting in the, but this is every square meter, and this is a 24/7 number. And to give you a perspective, these scenarios we're looking at for greenhouse futures are now, at least in the latest generation, they're called RCPs, representative concentration pathways. They are numerical, so we have RCP 2.6, RCP 4.5, RCP 8.5. Those numbers are equal to the amount of imbalance in 2100 in watts per square meter. So we're starting at about 0.6 of a watts per square meter out of balance and looking to a future that optimistically is 3 or 4 watts per square meter out of balance by the end of the current century. So it's an enormous change in the Earth's energy balance. And of course, what is the way the system responds to this is that it warms up so that eventually it will reestablish an equilibrium, so the amount that is leaving is equal to the amount that goes in. And how much does it warm up? Well, it warms up to the point where the terrestrial radiation that it emits makes that balance. The amount that it emits is proportional in some sense to the temperature of the Earth. So the temperature has to increase to make that balance. Well, this is another one of those hockey stick curves, and this happens to be global temperature that's been reconstructed over the last 1,000 years or so, and there's a fair bit of natural variability even in this period that's relatively quiescent, where the sea levels rose and then they kind of stabilized, and it looked like there was not much going on. Temperatures have wobbled up and down, so there's been little ice ages, there's been sort of thermal optimum periods and so forth. But then in recent decades, we've seen this unprecedented, very rapid rate of warming. And zooming into this, so this is a thermometer record. What I just showed you here was largely a recreated temperature record from proxy indicators, tree rings, corals, isotopes from various natural recorders in the system, and then people have translated that into temperature over different locations over the Earth's surface, and then they've aggregated those to make a global total. In this case, these are actually records of temperature on land and at sea that have been compiled and quality controlled and so forth. This is what you would just call the average global temperature. So it's all, in this case, it's just referenced to 0. But what you can see is that since the late 1800s, there's been a pulse of warming, kind of a stable period, ups and downs, and now something that looks like it's really getting active. It's this period since about 1970 where from the amount of greenhouse gases in the atmosphere, it looks like this imbalance is really starting to play a role. And there's a community of climate modelers that actually have interrogated these kinds of records. One can use global climate models and replicate these ups and downs, not in every detail, but at least in broad detail, up until about this period, if you do not introduce greenhouse gases into the system. So in order to replicate what we're seeing really recently, you have to introduce greenhouse gases into these climate models. And indeed, they reproduce this pretty well. So we're very confident that what we're seeing in recent decades is the fingerprint of human-caused climate warming. We can actually analyze carbon dioxide in the atmosphere and detect the signature of fossil fuel. So there's different kinds of carbon depending on the isotopes of carbon, and it's very clear that what we're seeing in the atmosphere is this loading from essentially industrialization and our increasing use of energy on the planet. We look at a family of climate models. We don't usually rely on a single model. It's kind of like the stock market. If you're looking at stock market futures or even an understanding, usually you listen to a variety of pundits and then you kind of process that. And that's what's been done here. So in this case, there's over 30 of these climate models that go back to about World War II, and they're run, actually the models are run retrospectively as well as prospectively. This happens to be for the statewide area in California, and the different shading here is, for blue, this is one of the sort of more moderate greenhouse gas emission scenarios. I mentioned this RCP 4.5. That's what that one is. And the red is one that you might call business as usual in a high fossil fuel society, because this is a global result. Everybody shares the same atmosphere. The atmosphere is well mixed. We can't, unfortunately, we can't block off Long Beach from everybody else and solve the problem here and not be influenced by the rest of the world. So that's this is a global problem, which makes it difficult. So if you look at the resultant prediction of future temperature run by this is a sort of consensus, the median of many climate models. You can see that the result for the maximum statewide maximum daily, so the afternoon temperatures in California would probably increase by something like 5 degrees Fahrenheit over the yearly period, whereas by the end of the century, under this higher greenhouse gas scenario, we're looking at an increase of something like 10 Fahrenheit. To give you this a sort of a rule of thumb about the consequences of such an increase, we paid quite a bit of attention to the snowpack in California because it's a water reservoir, and in California we have approximately a year and a half of storage of a year and a half of runoff worth of storage in our built reservoir system. We don't have the big Lake Mead, Lake Powell types of reservoirs on our system. So snowpack is a big deal because it's delivered in the winter, and then it gradually, not always so gradually, but in general pretty gradually runs off in the spring and summer period when it's really needed for domestic and particularly agricultural uses. We reckon from looking at hydrological model calculations that for every degree Fahrenheit, we lose about, I have to do this because I usually think of this in Celsius, but a round number is that for every degree Fahrenheit, we lose about 8 to 10% of the present day spring snowpack in California. Now, that doesn't mean we lose water, but what it does mean is that water is not stored up there in the spring period that will be then exploited for water resources. So we're going to have, as well as a sea level problem, because of course as the system is warming, the oceans are rising, but also we're incurring a lot of other impacts, such as the snowpack, which then becomes a much more volatile, flashy kind of system that produces more runoff in a given storm in the wintertime. Our reservoir system in the state is used not only for catching water, it's also used to hold water back because we need flood protection. And that means that we can't afford to fill up those reservoirs in the middle of winter because there may be another storm coming. So we have a lot of challenges that we're going to have to contend with, and whether we're on this temperature trajectory or this one is really important, because this one is going to be terribly hard to contend with. The other thing that's noteworthy here is that these two scenarios, so this one, a relatively moderate greenhouse gas emission scenario, and this one, sort of the business as usual scenario, you don't see much difference in in this one index, which is probably the easiest index we have, is just the temperature over the state or over the globe. Really doesn't start to diverge until sometime in the middle of the century. So that means that you have to kind of take it on faith that the actions you do to mitigate this problem today are not really going to be recognized and felt until decades later. So this is a really difficult challenge for science, because we have to convince decision makers where an election cycle is sort of a short period compared to that, and a lot of politicians just frankly they don't care what's going to happen 3 administrations away from them, because they're out of office and they have tons of immediate problems that they have to address. But societally this happens again and again and again, and in some sense the same kind of thing sort of inhabits the discussion that Ron was pointing to about we have to start thinking about our strategy so that when the time comes, there's an option, that's not so draconian in dealing with the future. Okay, so back to sea level. I'm filling in a little bit because Ron stole a lot of my thunder. You know, he talked about all the elements in sea level that I was gonna say about. But anyway, so if you look at the sort of prime causes of sea level rise, and you exclude sort of immediate geological influences, such as plate tectonics, and we're still actually on Earth. We're still reacting to the unloading of the continents from this big ice mass. So the crust is still reacting. It's called glacial isostatic adjustment, and but most of the broad scale sea level rise that we see over decades is caused by two different influences. One is the fact that as the oceans warm, they expand thermally. The water is not incompressible, and it's like air in a balloon. If you heat the air in the balloon inflates. And same thing happens with the ocean. And through much of the 20th century and before that, the ocean volume was expanding because oceans were getting warmer. But then there's this second mechanism that's coming into play, and that's the fact that this ground-based ice, like the ice in mountain glaciers and the ice that's harbored in these big sort of mega blocks that constitute Greenland and Antarctica, are giving way and melting or slumping off. And so that's just the introduction of more mass into the ocean. So those two mechanisms are the primary ones that are going to be felt in the decades to come. Now, if you're living in a particular location, Long Beach had a lot of oil extraction in the old days, and there was consequences to that and so forth. So there's local stuff going on along the coastline too, but the big scale problem is these two factors that relate to climate warming. So the state of California, of course, is one of the, I think, I would say more progressive examples of communities, states in the nation that are thinking about climate change. And recently, the state decided to update its guidance to state agencies, amongst them the one that Ron works for and many others, on what to think about in terms of sea level rise along the California coast. And so this report, Rising Seas in California, is sort of the science underpinning of this updated state guidance, which just came out, by the way, in the last week or so. I just received a copy. So there's this science report that has lots of fine print and so forth that establishes sort of the whys and wherefores, the fact that new science is emerging, the fact that we're pretty certain that sea level is going to rise, continue to rise, not fall over longer periods. The fact that globally there are some signals that are appearing that are problematic as far as sea level rise. And finally, the fact that even though there's a broad range of possible outcomes in sea level rise over the next century, it is going to rise, and it's not prudent to just, as Ron said, just ignore it. He had that picture of the Volkswagen that was, an example of that strategy. So here's a picture of, this is global sea level, and this is what we've seen in the period since about 1990. So as I was saying, the biggest contributors to sea level rise are this thermal expansion component and this ice melt component. And the point of this picture is the fact that the thermal expansion component, and if you add to it the ice melt component, you get pretty much the total sea level. But this is no longer rising at a rate that is greater than the ice melt component. And you can see, at least broadly, that it looks like the ice melt component is getting big. And it's the recognition of that process right there, because as Ron mentioned, the amount of ice that's potentially available to increase sea level is tens of meters. It's enormous. And this thermal expansion, even though it's consequential, it's not going to be tens of meters. It's going to be fractions of meters in the future. So the big gorillas in the sea level world are these big stockpiles of ice that we have in high latitudes. And what we know from recent observations is that Greenland is losing mass. It's melting, and West Antarctica. So these are two pictures of the two poles. Is losing selectively in this area that's outlined here along this the West Antarctic coast, and to some extent this peninsula. And in particular, this area, because it houses a lot of ice, and because the form of the loss of ice in this area tends to be more mechanical, that is, big ice cliffs slumping off and not waiting to just drip, drip, melt, melt, such as is more occurring in Greenland. That this in recent few years has been recognized as a big problem area in terms of global sea level rise. So Ron mentioned that there was 70 meters or so of sea level rise that's potential if you melted everything. Well, this is not 70 meters here. This is probably 5 or 6 meters. But if you lost that in a hurry, 5 or 6 meters is a big sort of change that would have to contend with. There's about the same amount of ice that's available in total from Greenland, but physical modeling has sort of tried to understand how fast we could lose ice on Greenland, and the results, at least at this point in the game, seem that the ice loss in Greenland is a sort of centuries, multiple century scale problem, whereas this one seems like it could happen faster if the climate were sympathetic to that. Dave, how are we doing on time? 2 minutes? Yeah, that's my friend down there talking. I didn't say that to him when he was blabbing on about the peninsula. Okay. Okay, so I mentioned that that this ice loss in West Antarctica is potentially really important. And there's been one recent modeling study by Rob DeCanto and his colleague Pollard, who found that if they instilled new kinds of physical mechanisms in their ice loss model, they could replicate better the kinds of ice loss that was evident from some of these paleo observations. Ron was showing you some of that, where there was from observations that have been collected from sediments and ice cores and so forth, that it's recognized that you could lose quite a lot of ice and you could gain a lot of sea level in a relatively short amount of time. And this model, amongst other models, is better able to replicate what we saw in the period before the last glaciation 200,000 years ago, and this ancient period 3 to 4 million years ago, when the Earth was quite warm. And so there's some compelling features to this new modeling result. The new modeling result is really important because it sets the potential for sea level rise to be much greater, another meter or so of rise by 2100 than previous estimates had indicated. So the other thing about sea level rise that's kind of interesting, it's a bit of a secondary effect, but it's not negligible, is the fact that as ice and mass is lost from Antarctica, in this case West Antarctica, there's gravitational responses, so the actual pull of gravity becomes less around the Antarctic continent and correspondingly greater in the far-field area. So it means that even though Antarctica is the area that's losing a lot of mass and putting essentially water into the ocean, it's not going to suffer the amount of sea level rise that the rest of the global ocean is because of this gravitational response. And these areas along the northern continents will actually have increased sea level rise because of this far-field effect. So that's another thing that we have to think about in this longer-term calculation of the sea level rise problem. So here's sort of it's almost a cartoon, but I think it's worth looking at. This is actual observations from, I think it's from San Francisco over the last century or so, or it might be global. I haven't read my own literature here, but it hardly matters. And then here's what is reckoned to be possible over the next century or so, using different forms of estimates. This one using a more ecologically friendly emission scenario. This one being one that's less concerned about that. And you notice that this is in millimeters, so this is 1.5 meters. And now what I would like to point out, see, we made this picture 5 or 6 years ago before this new modeling result, and now the upper end of all this is sort of up here rather than down here. So there's this in the Rising Seas report. There's even though it's we didn't want to overly rely on this new modeling result, we felt that it was prudent to introduce what was called an extreme sea level rise scenario, this so-called H++ scenario. Don't ask me where that nomenclature came from, but it introduces what I would call a very low likelihood, but of course very heavy consequence. So the risk in Ron's parlance there, where he was defining terms, it's one of those low probability but very very high consequence cases. So it's kind of up to you whether you want to pay attention to this sort of way outside scenario. But if, for example, you have a lot of economic or human capital that's right on the coastline, that might be one where you actually might want to think about. So this is again sort of a cartoon graph where this is what was previously used by the state of California for sea level guidance. Something that went from here to there and sort of a midpoint about 3 feet. So these are feet of sea level rise by 2100. And this is this new result from the Rising Seas Committee where instead of providing a high and a low and kind of a middle, what the committee did was they formulated these possibilities based on which emission scenario would be occurring. In this case, this is the one, a very optimistic scenario, RCP 2.6, and this is the unfriendly business as usual scenario, 8.5, and then up here is this extreme scenario. So these are cast in sort of attempted probability ranges. So this is the 5th percentile and the 95th percentile of under this emission scenario. This is 5th, 95th, and you can think of this as 99.99th or something like that. But it's sort of the highest physically possible scenario. I'm going to skip these. The only thing I would say is that even though these graphics that we've been throwing around have mostly stopped in 2100, sea level rise is not an issue that's going to stop in 2100, because the consequence of having a warmer Earth is that this grounded ice, this high latitude ice stock is going to continue to melt. And so this is going to be a multi-generational, multi-centennial problem that we're facing. And one way to think about this is it's not really a matter of if, it's a matter of kind of how fast and when we're gonna see certain forms of sea level rise. Another one of these, another one of these pictures of different scenarios. I'm not going to belabor that. All I would say is that in the Rising Seas document and in the new state guidance document, they have tables, and you can place your odds on which emission scenario that global society is gonna follow. And if no one really knows the answer to that, but here's sort of a middle ground, and that one lays out the odds of sea level rise, in the sort of middle 67%, if you want to put your bets there, and so forth. And then it also has values for the outer edges of probability and so forth. And it does it for different points in time. 2030, 2050, out to towards the end of the 2100s and so forth. It also gives you an idea of, if you have a seawall that presently is this high, how likely is it that sea level will exceed that at a given point in time? So that could be helpful. So I want to close with just a few shorter period sorts of observations. One is that, as Ron was pointing out, sea level along the West Coast has lots of natural variability. And it's interesting that if we go back to the last really large, important El Nino condition that we had in California, which happened in 1998, and we look at sea level since then up to about the year 2013, it turned out that there wasn't much sea level rise at all along the West Coast. These red colors are kind of intuitive. Reddish is lots of, a relatively rapid rate of sea level rise, and blue is negative sea level rise, sea level fall. We were in the sort of pale area here, which meant that, nothing really too much was happening. The Western Pacific in low latitudes was rising at a rate that was about 3 times the global rate. And that pattern is thought to be a result of the sort of Pacific Basin trade wind extratropical westerly systems that was essentially pushing water around. And now we think that this pattern has relaxed, and in 2014, we started to see sea levels rising again. In fact, in La Jolla in November of 2014, we saw the highest sea level recorded on record at the pier at Scripps that year, which happened not with under conditions of a huge storm, such as happened in January of 1983, and another sort of inside baseball story is that Ron and I in 1984 actually wrote a paper about this this episode where we had a huge El Nino in 1982-83, and we had essentially gargantuan winter cyclones that were crossing the North Pacific Basin. This is a scene from the Monterey Bay area where waves were crashing into the coastline over the rooftops of these houses at, I think it was Aptos development up there, and then running back through the houses to get to the ocean. There was a lot of damage along the California coast at that time. This is a storm similar to the one that occurred on the 27th of December that year. But the lesson is that, as Ron mentioned, it isn't that still water sea level rise that's going to create all the problems. It's when that is coupled with these big disturbances. And in our case, usually, not always, but usually it's a winter storm. Now, somebody else, one of the residents was saying how there was a 1939 episode, but that was actually a tropical storm that occurred that issued a lot of damage. But by and large, it's these winter cyclones that occur. And when we look at the big sea level extremes along the California coast, I know this is a record from, where is this? Help me. This is La Jolla. And this goes back to World War II. So we just counted up the number of extreme sea levels above, I think it was in the 1 in 10,000 hours sort of extreme, you see that sea level problems don't happen every year. You know, there's a lot of years where there's really not that much going on, but there's some years, and in many cases, these are the El Nino years where the storminess is really activated, and there's also this effect of higher waters along the eastern boundary of the Pacific Basin, in other words, the West Coast, that we can get all these extremes. So we have not seen a winter like 1983 or, arguably, I guess, 2005? You had a scene from that winter, I guess, Ron. But we haven't had anything like this in the last few decades. And to some extent, it's sort of a luck of a draw. This is the water level picture. I think this is right from the report that we did, Ron, that it shows on 27 January, where in this case, I forgot to look at which station we looked at here. Is this San Francisco? So San Francisco was seeing the maximum daily observation of still water sea level, not the wave generated stuff, but just the water in the stilling well, was about 2 feet above tide prediction, above the maximum tide prediction. And by the way, that happened on a day that was almost the maximum astronomical tide for the month of January. So we just, we got a bad draw on that particular storm. So that's the points of my talk are that it's happening. It's going to be increasing in the rate of sea level rise that we see not only globally but along California. And essentially, even though there's a lot of uncertainty, it seems that waiting is just not a really good policy. So I'll stop there.